So, okay, so hello everyone. I hope you enjoy your time during this ISSP 21. I'm sorry to not be able to be there during this occasion. I would like to thank Simao and Magdalena for this invitation to give a talk on thermodynamic data mining and data curation. And basically, we discussed, I think, 1 month ago about these meetings and about how to conduct such a workshop. I really enjoy it. I really enjoy Zednek Wagner's, Earl, and Vladimir and Allah talks, which will help me to present mine. So, okay, now. So the content of my talk I will start with some definitions of data mining and data curation. I will give some example of papers that they use such strategies, and I will follow with some models that we develop using artificial intelligence for predicting some ionic liquids properties amongst categories of novel materials. Yeah, so if I start with the first point is what is the thermodynamic data mining? So, and basically data mining involves extracting valuable insight and pattern from large data set related to thermodynamic processes. And this is done normally to check patterns, correlations, anomalies, and trends in various data sets. So as already mentioned, for example, by Zednek or Vladimir today, so sometimes it's hard to evaluate errors within a data set or between data sets, and by using, I would say, a statistical or non-statistical analysis amongst other mathematical techniques. And basically, within the data mining, what we'd like to do is to extract useful information and develop knowledge from raw data. It's explaining why raw data are very important. And of course, there is various techniques to be which can be used to classify clusters or associate or regress data. And a few examples for thermodynamics could be related to material properties prediction, for example, like determining melting point or heat capacities and so on, as well as phase diagram construction. And a lot of software are now used, for example, for alloys elements, like using CalFAT methods through thermocal as an example, and as well as different modeling and chemical reaction approaches combining kinetics and thermodynamics properties in order to fine-tune, for example, a reactor size in using Aspen as an example. And this example just illustrates how data mining can be applied to thermodynamics and extract very important insight to innovate, I would say. And if now I'm moving to the step-by-step process, of course, prior discussing this different step, we have first to ask ourselves, what is a problem definition? So we need clearly to define the problem. What is a goal, what we would like to achieve thanks to the data mining? Then we have to proceed with the data collection. And data collection, of course, we have to use various databases containing a very large set of data set from different, I would say, coming from different equipment, especially when talking about thermodynamics properties. And of course, we have to clean the data somehow, and different techniques may be used. And within our groups, and thanks to Magdalena and Zednek collaboration, we did try to recommend data using genostic analysis, as well as statistical, I would say, as well by analyzing statistically the data, as many authors are doing. Of course, when we move to we run the data collection, then we have to do a data cleaning and data integration as well, prior to move to the data transformation. And data transformation is very important in order to get a suitable format for analysis. For example, to have the same units and blah blah. To run normalization as well, and to get aggregation of variables. Data reduction is something that we are quite often doing by pure processing data mining processes, and in order to reduce the volume of data while maintaining the integrity of and relevance of the data, which is quite also very important. The data mining is really touching this point 4 in these figures, in which we want to really apply different techniques that I will carry on later on in order to get a proper pattern evaluation in order to evaluate a given properties and so on. And further point could be then related to the knowledge representation, deployment, monitoring, and maintenance of the data in order to involve different aspect of the data, which will be related to the data curation. And of course, what kind of tools we can use. And I present some pictures here just to present some software which are normally specialized tools, including thermocalc, as I already mentioned, using CalFAD methods, MATLAB, or also Python, which is now well defined, and by using also a scientific equation which can be implemented within Python. Weka is another example, which is widely used in order to develop a neural network model, as well as Jupyter, which is combined with Python. Of course, a last but not least example is open access sources like OpenThermo or other software or add-on, which can be used in Excel or and so on, which may be used to run such a data mining analysis, I would say. What kind of techniques is often used for the data mining? This picture is from Munster universities, and in which we have different kind of tools which is used, and the most often used is a regression analysis or the clustering. We cluster the data, and we can classify as well, depending, for example, of the thermodynamic stability of or phase at different temperature could be used to classify material. We may use also in combination neural network in order to develop algorithms which may develop model for given properties. Of course, we can combine with DFT calculation, Monte Carlo, or other MD tools, which may be also very useful to implement or complement data, experimental data already obtained within a database. And based on this, we may be also able to design and develop what we say decision trees and association room meaning in order to identify association between different thermodynamic properties, which may be very useful when we want to develop an in silico formulation of novel material, which is quite very well widely used techniques, especially for dipotectic solvent or ionic liquids, I would say, or any solvent which may be substitute current solvent used in industry and banned thanks to the or caused by the REACH rules, I would like to say. And if we look at challenges with this, of course, many challenges were already mentioned by colleagues in this workshop. One of these is data quality and pre-processing. And data quality, what we say, data is always coming with errors, and the errors must be quantified in order to double check its quality. And other point which made data mining quite challenging is privacy and ethics. And I think Nista and Vladimir discussed about the public domain and private domain, so which is also provide some challenges with the data mining. Unbalanced data. Sometimes when we want to develop a model, for example, at high temperature, high pressure, sometimes we find some difficulty to get data at very high pressure or pressure higher than the pressure that we want to set to any process, which may the scarcity of data for our condition very challenging for data mining. And impact of this lack of data, it's which can this can lead to major errors, because as Vladimir say, the end user will be engineers. And engineer, if they do not have data within the condition that they would like to apply it or to extend the data, this can cause a problem with evaluation of data or prediction or scales, and also other errors which may impact the end users. Noise and outliers is also a main challenge with data mining by developing data mining algorithms, which may cause inaccurate pattern or model. This a few examples. So, as you may say, the quality of the data is one of the key aspects. And one thing before developing model by thanks to this collection of data or prior to do any data mining, one should assess and recommend data set. This is also a key recommendation. If now we move to the data curation involves a systematic collection, organization, and maintenance of the data. And basically, this is huge different, because before we discuss about the significance of the data. So now, how we ensure the data are accessible and usable and reliable. This is very it's another very important, which is related to the data curation. And of course, if we are talking about thermodynamics property, we are talking about databases, because there's a lot of property which may be covered, including, for example, enthalpy, entropy, gift-free energy, just a formation of material, just to cite few, heat capacities, and phase change temperature and pressure, critical point, and so on, which may be accessible to any people that they would like, for example, to do equation of state model. Of course, we need also to make this thermodynamic data in a standard model, means within the same units and along with the old database. For example, to make a standardizing calorimetric data from different studies, to make them comparable and easy to use, for example. And then in terms of the example, we can one can discuss also the metadata and annotation, and this is done in the context of users which whom may be able to understand and to evaluate the reliability of the data and reproducibility of the data, which is very important. And the metadata and dataset must be as user-friendly as possible to help people to use and to implement or manage the data. Another very important point of the data curation related to the data mining, it's validation and the preservation of the data. And one point that Vladimir highlight without really saying, and it's a lot of papers coming from the, I would say, the 2000, 2020, the last 2 decades, I would say, and many journals start to ask authors to do not duplicate between numerical data and figures. So it means a lot of data points, numerical data, were lost. And now a lot of groups try to collect all graphics and try to, thanks to artificial intelligence algorithm, to recollect data point from graph. However, in some cases, it's very challenging because of the low resolution of the graphs. So this, I would say, it's highly depending on the quality of the pictures or the figures that also authors share with the community during their paper. And this will give a direct link to the long-term preservation of thermodynamic data, because if we can collect historical data, we can compare with over the time, for example, the quality of the measurements, especially for reference system, which must be used to calibrate equipment. So means by asking authors to report on their calibration, for example, DSC or any solid liquid equilibrium equipment, to report a reference system. This could give us an idea of the long-term preservation of thermodynamic data, but also to look at the error correction or uncertainty, I would say, related to specific techniques if people are developing in-house techniques, for example. Curating data are also very well used for computational thermodynamics, including also the development of force field. When we are talking about enthalpy of vaporization or density, they are quite often used in MD to fine-tune force field. And this is also very important that they are in open access in a way, and also access to get recommended data in order to get a good integration between experimental and simulated data. And this is quite very funny, because sometimes people are using MD and develop force field, and they use a density, for example, to assess their simulation boxes, which is totally nonsense, because density cannot be used to evaluate the MD simulation or the quality of the MD. Anyway, what is data curation? And I reflect in this slide 10 points, and these 10 points we can debate during hours and on their importance, but just by not in order of priority, but I will move from the 10 to the ones in order of priority. And the first point is ensuring data accuracy and reliability, which for me is the more important point, and the more important aspect that each database should highlight and report for each any data point, I would say. And of course, data curation are very important also for the reproducibility in research, and that explaining why many grants request to get access to any raw data. And we can only encourage all authors to report into their support information any raw data which may be unseen sometimes in many papers. Like, for example, when using vibrating tube densimeter, like the frequencies as an example. And this is quite also very important, because sometimes people are making errors by converting the tau to raw due to poor calibration, and or only one substance is used to calibrate it, or to verify the density, also the quality of the density of the equipment anyway. And of course, the point number 9, it's the consequences. It's a facilitating innovation and discovery, because when we have a good I would say metadata or databases which are interconnected with data inside of the data well established, and we can develop model which are very useful for the end users, as already mentioned by colleagues. So if we are talking about the steps of the data curation, it's a life cycle, okay, and it's not a linear processes, because we want to implement in order to maintain the integrity and the usefulness of thermodynamic information within the scientific and industrial sectors, which move from, again, when we are doing a good data curation, what is the research question behind this? Which kind of data we are looking for, and how to use it, how to develop a data management plan in order to have a user-friendly interface, which for them to be able to read and use the data, and how to archive the data, and so on. And in terms of tools, again, there is a lot of platform. I would say TD as a thermo data engine is one of them, as discussed by Vladimir. There is a lot of open source, especially for I would say microstructures or quantum chemistry-based information. There is also open material database, which contain material design and computing help. Among software which are not free or of charge, like Thermocalc. Thermocal contain a massive database for inorganic organic and inorganic compound. We have also a thermodynamic table, TRC, or niche journal thermochemical tables, and as well as other software which may be related to a database, in-house database created, like a Panda software, which may be useful because it can be connected to through Python to develop artificial intelligence model. Material project is also well established tools which may be used to optimize, for example, thermodynamics properties and model. So now if I'm thinking data curation, if we are just thinking a minute, so data curation, it's a foundation for effective data mining. So without a data curation, we cannot, I would say, boost up or have effective data mining. And the combination of both ensure quality of data for better mining outcomes, I would say. However, we do need to make a feedback loop in order to get to provide a guide for data curation effort. And this now I will just carry on very quickly on some example of literature papers. I will not go in detail because I do believe you are all already exhausted. And if the first example is just it's a graphical abstract from papers. I report the reference behind. And this is an example of how we can move from images to data curation to diagnostic of errors. This was a full diagnostic on the different motors papers, and the authors developed a very well integrated model by combining data mining curation with a deep learning approach with ANN model in order to predict to run some prediction. Another example, it's on the formulation or reaction pattern on some chemicals, so iron oxide here, which is prepared by co-precipitation method. And within the method, the authors try to use artificial neural network in order to fine-tune the composition and the condition in order to get as pure as possible iron oxide at the end. And another very well established example is from medicine, and because artificial neural network, it's or I would say data mining, data curation to develop model are very well established, and especially when trying to develop some good drug deliveries, as this example display within this graphical abstract, where by highlighting the data mining curation methods and data analytics used in order to make a predictive method for delivery of drugs within rats or whatsoever. And finally, this is my last example before to move to the case studies, is this paper is really developing how deep machine learning could be used to combine molecular descriptors from, like, for example, the shape of catalyst, the moiety size, particle size, charges, to define different prediction onto again medicinal aspect. And the author did try to evaluate or to move from input to outputs using different deep machine learning approach, including random forest and neural network, to cite only two, in order to fine tune and to help end user to make a decision. And within this, people are normally using a very user-friendly interface in order to make end user GUI interface, which may be used by people that they know nothing about chemistry, they know nothing about physics, mathematics, or IT, but they just want to use a software in order to take a decision, make a decision. Sorry, and this is exactly where we are moving actually within my groups. So we do try to develop model and to an interface which may be used by any scientist, even if they are not from thermodynamics, to take a decision, I would say. And this in this example, in my group, what we did is to define, as an example, a deeper technique solvent, which may be very useful for, I would say, carotenoid extraction from plant. And this was done with people from pharmacy, and they know nothing about thermodynamics, but just to develop a model. Anyway, so this is short stories. And now if I'm moving to the case studies on property of ionic liquid, I promise to be short. Of course, since the beginning of my PhD, I started in 2002, so it's a long time now, so 22 years ago. My supervisor asked me to develop a database for ionic liquids, combining pure and mixtures and a lot of properties. So, and the idea was to develop and establish and develop models. And of course, we use that also to try to understand the effect of impurities in ionic liquid, because they are affecting a lot their properties. And just to give some numbers, these are not up to date, to be honest. But what we did is we found a way to extract all data from IUPAC database, from IEL Thermo, I would say, and to get in a readable format that we are directly using in Python code. So we're just creating CSV that we collect data from any database, I would say. It's working also with Dortmund database for the from the, I would say, public part, because I do not have access to this. But we find a way to create a code to extract data from any website, web page, as well as from any PDF, I would say, document, and to develop CSV file per category. So, and thanks to artificial intelligence, we find a way to, for example, to include into one CSV only density data, and from the same paper we have another CSV which contain viscosity data and so on. So today I will discuss only on density viscosity because the time is short. And just to give you an idea, so we extract the data from the NIST database, and we implement into our Python code, and we explore data analysis. So, and in order to get what type of variable analysis or what type of variable we need to consider by looking at the density. And this is just an example for the plot is a specific, it's a density against temperature. And here we have different pressure, and it's one kind of ionic liquid. It's a butane methyl hexafuel phosphate. My memory is correct. Anyway, and basically what we can see, what we did, we extract the data from the NIST, and then we ask, we develop a code which gives a correlation matrix, which gives the significance of parameters within the properties. Okay, so basically the density is strongly affected by the pressure, and less by the temperature, a little bit less by the temperature, and so on. And due to simply the pressure range and so on. And then based on this, we can have an idea of the descriptor which may be used within any neural network development. But before to move into this, we need to have an idea of what is the meaning of the properties. And directly for from this data extraction, we can get a parity plot, and this is a density at atmospheric pressure as a function of temperature in Celsius, and viscosity is the same for the same ionic liquid, C4M and PF6. As you can see in this parity plot, in this plot, we have some data which are very outside what we can expect from the uncertainty of the density, which normally should be in a bracket of 0.1%, according to the equipment. And for the viscosity, it's even worse. We can go up to 50% deviation from average values, of course, and the deviation of the literature point from the literature. And then, as I mentioned, thanks to Magdalena and Zednek, we run also previously for the viscosity, but also for the density, the genostic analysis. And this is just to give you an example how we are using it to get recommended data. And here we have the weight function of the function of temperature for the viscosity according to the viscosity of the C2MIM triflate with a different literature data set anyway. And what we can see really from this graph here is the cross looks like the best set. And the cross are coming from the group of, if I do not say, Cucino, from the group of Cucino. And this data should be recommended. However, for low temperature, for example, for temperature lower than 290 Kelvin, one can consider that the data point, the square data point from Rodriguez et al., could be used as a reference one at 0 degrees Celsius, and not the data from Cucino. So from this analysis, what we did basically is really instead of looking at the data set and all data contained in each data set, we extract a data point from different data sets, and in order to get, I would say, recommended values. And based on this recommendation, then we develop model. And we did that for viscosity but of ionic liquid, but also for the density. But this model were developed not by using, I would say, a machine learning approach. So now we decide to move to the machine learning approach by using the same philosophy of analysis of the data. So first we analyze the data, we get data recommended, or we use sometimes all data that we can collect, and then we try to use artificial neural network. The main problem of the artificial neural network is we can calculate what we want, and based on any equation, because we can use a number of parameters that we want. But what we decide to use is a mathematical modeling approach, which is based on physics plus machine learning, what we call the scientific machine learning approach. And by combining machine learning approach plus scientific understanding, we can develop more robust model. That's the purpose. And basically, what we did, we use a multi-layers approach within neural network, combining with a physics and sphere neural network with a different wave function, which are combined in hidden layer, sorry, and we put several input. For example, for the density, we may need the chemical structures, we may need the temperature, we may need the pressure parameters, and so on. And we have as output, we have directly the density or other volumetric properties related. Of course, because we want to do something which is physics and sphere, or based on physics, we decide to use the Tate equation in order to get a roof, some physics behind, because this equation is very well used, I would say, to correlate three-dimensional density data, which may be as function of temperature and pressure. And of course, one can argue also to use bulk modulus model, like equation of state in order to predict also the volumetric properties by the sound knowledge, for example, of atmospheric pressure. That we did a publication in this 4 or 5 years ago anyway. But we decided to move to this with this equation that we implement into our model. Of course, we need a starting ID. Then we have the data recommended. We have the data curation down, and we carry on now with the equation that we want to use as function of temperature and pressure. So then we need to ID to develop model, and we start with effective volume of ions, the definition that done by Rebello in 2002, I think, papers, based on the near ideality of ionic liquid, a mixture of two ionic liquids. Anyway, so the knowledge of one effective molar volume is enough to define the other just by sample subtraction. Then, based on this, we define what we call the effective molar volume of ions as a function of temperature pressure. This is the same approach as done before, but now we implement this with machine learning. And now, just to give you an idea, I compare the black dot is my previous model that I published in 2008, I think, and the red dot is within the same data set, within the same equation by using artificial intelligence modeling. So means we improve by a factor 3 or 4 the quality of the model, which is quite impressive. And by the same way, we observe the same for another. Sorry, this was for one kind of an ion. This was observed also for PFC-based ionic liquids. And again, this show how physics-induced neural network approach could be used to develop a model. But of course, this can be done only if we have data that they are correctly assessed. That is very important. And just to finally finish with this, so I compare this evaluation done by artificial intelligence with a PINN model by looking at binary system, ionic liquid plus ionic liquid, and with the data point reporting literature available in the NIST. This work is part of the Kinsley Omega PhD thesis, and one can see clearly whatever the ionic liquid mixtures that we are looking, that the model developed during this work is far better than other model available in literature, except probably for these mixtures that domain scale papers probably better. Anyway, the last two with the BF4. I do not know why, but most probably because they use this data to correlate their model, probably. In conclusion of this approach, this case study, so we develop several models for ionic liquid. I present only ionic liquid, but we did the same for deeper technique solvents. By comparing, I would say, different approach, neural network and physics-informed neural network, and one can see clearly the physics-informed neural network provide a better accuracy according to the data, and far better than the good contribution method that I developed before. And the same for viscosity. I publish, I extend the unified visco model for ionic liquids, and by using at least neural network approach, we have far better uncertainty of the accuracy of the model. And now with the PINN approach, it's even better. The same for the conductivity and for the speed of sound. We obtain, it's mainly correlation because of the lack of data, especially the speed of sound at the high pressure. We obtain a good result for the properties. So in conclusion, I just took some pictures, not mine, from the internet. That's why I put some references. And now, in terms of the world is moving and combining artificial intelligence and scientists, and we need to have really a clear control of this, especially for people that they understand the properties. Of course, we need people that they master data cleaning and data processing, which are very quite important, especially for the end user. We need to prepare people for machine learning, and especially people that they should have a double competencies, one in physics or thermodynamics or whatsoever, and in IT. And of course, it's a looping process. So we need to get people to be able to run the data acquisition, management, data analysis. Of course, teaching is quite very important, and to get new ideas. I finished with my presentation. I do hope I was not too long. So thank you very much. I hope it was clear.
Thank you, Johan, for this fascinating contribution. I think we're all tired, but we followed.
Yeah, I do believe so.
No, we followed through quite attentively. So I now open the floor for questions.
Thank you. I want to say this was wonderful presentation. Thank you, especially for scientists who want to connect experiment theory and machine learning. And I have one short question. In the beginning, you mentioned Python. And
Yep.
is which library you prefer if you want to use Python? And when we talk about ionic liquids. Thank you.
Okay, we are testing different library, but SCI Python is one of them. For Python, it's very well established now, and you know, if you want to do a neural network and all is included in the library now, honestly, and you do not need to have a huge background in computer science, but this helps, I would say. And now I'm running in Mac within Anaconda, and it's even easier.
Okay, thank you. We have a question from Vladimir Dickey, which risks to be a bit controversial to you. How much are you involved in deep eutectic solvents? Would it make sense to run a comparative study similar to the one for ionic liquids initiated by Ken Marsh 20 years ago, or create a public database similar to IL Thermo?
Yeah, I agree. I agree that something must be done in the protective solvent, because this it's open doors for many errors. Let me explain why. Because now people from non-specialists on physical chemistry start to look at what they call a natural deep protective solvent and solutions that they are not at the eutectic. Okay, so they're calling NADES or natural deep protective solvent for any binary mixture containing natural compound that they are not necessary at the eutectic composition, which is quite controversial. And people, I do believe, and I do agree what you said before, and I think a lot of people do not understand what the different, what is deep. First, what is deep, and what is an eutectic. And some people, because in some mixture you can have a depression, or you can stop to see any melting point. You can just have a gas transition. This sometimes occurs as well, especially in natural compound. And what is the impact of for example, water? And because when we look at the natural compound, we can cite a glycerol or as an example, or of compound or mantle, L-mantle, which is quite often used. And even if it's a hydrophobic compound, it still contains water. And the same with large carboxylic acid, like octanoic acid, because this is quite often used because of the fatty acid that they want to remove from plant. Okay, so people are using a long chain of carboxylic acid, saturated or unsaturated, if they want to, depending on the fatty acid that they want to remove from the plant. But this quite often create issues within the formulation. But I agree with you. So something must be done, and at least as we discussed, I will promote the journal, Magdalena, if you can, and with Earl, because we are here, we are free of. I would say editor of the journal Solution Chemistry, but it's something that we want to open very soon. It's at least a special issues on a technical solvent to provide a proper definition, and this could be the beginning of something, Vladimir. I don't know if you take my point.
I think so.
I don't.
How deep is your love? How deep is your love? Allah, the question.
I'm speaking
I
too
just
much. Sorry.
I just want to add what John said about the uh, characterization of this death. So you mentioned it. Water is a major impurity which can affect properties, but it's not the one of the problems in comparison to ionic liquids is the stoichiometry. So because they quickly claim 1:1, 1:2, whatever composition, but actually when the actual composition is requested and they show NMR spectra, it appears that the composition is far different from the claimed, and this information is frequently missing. So that is the one of the important aspects which is missing for DES is proper characterization of the systems. And for ionic liquids, I mean, traditional ionic liquids, it's not a big challenge because ions can form 1:1 or 1:2 depending on the charge of the ions. But the problem is with protic ionic liquids, where the stoichiometry becomes playing a role because one of the ion is hydrogen, not ion, but hydrogen may be not fully protonated. I mean, not hydrogen, the center, nitrogen may be not fully protonated. So that's why it doesn't, the stoichiometry may play a significant role in that case. That's why what is important for such databases, if you decide to go to that route, it's establishing well characterization of death and in general.
Yeah, but I agree. But just to say that we need to characterize the molecule before mixing and after mixing.
Yeah. Yes.
That's the problem, because people are just saying, okay, I use ultra pure blah blah, plus I mix with the other compound, but at the end of the day, you know, and all they store, you know, sometimes you can be very surprised because they are not thinking that that compound are hygroscopic. So anyway, so I do not want to say something else, but could be a very harsh, I would say.
Okay, another question from Earl.
Johan, I'll restrain from commenting on deep eutectic solvents. One of the things that you've raised in terms of curation, and I'm sure that everyone in the business thinks the same way, is the a method for assessing the data, throwing out the bad data, accumulating the good data, getting some reasonable assessment of what the uncertainties really are. But this is a huge undertaking. And it seems to me that the only way that this can be undertaken is through the use of artificial intelligence. Now, you've been working with artificial intelligence for a while now. Do you think that that is something that may come on the horizon? Because we simply don't have enough scientists to assess all of the rubbish data which appears on your desk and my desk and other people's desks.
Yeah, you're right. So yes, I think definitively, so artificial intelligence would be this exists already. I would for different aspects, like for example, in medicine, they start to be quite widely used, and for thermodynamics, say properties, I would say yes, but we need to get more information, because some property are dependent on on purities that they may affect some property more than the other. And it's not because the data is recommended from one author that another property may be recommended. You take my point? And it's the same with Vladimir, what Vladimir said before. When you compare the data set of different groups, we may have an idea of a good group or bad group or whatsoever without giving a black flag of any group. But it's not because a group is doing a good job that sometimes you cannot have errors within a data point of the data set. And I think ZNet shows this with the viscosity at the 303 Kelvin. And this was also reflected on the genostic analysis. So yes, if we have a program that they can analyze all data thanks to different algorithm, I would not go only for genostic or statistical or non-statistical analysis. I would do both, honestly. And because we are learning different stuff. And this could be done, yes, if the program are set properly. Because just to end up with this, what we are doing now is an interface for end user. And one of this is for metallurgy. And metallurgy, we know a lot of data available, okay? And and we develop a model which relate directly the tempering temperature and the cooling rate, okay? And the size of the microstructures, the grain size with the hardness, okay? Just a relationship between properties and so on. And this was conducted through artificial intelligence. And we developed a model which now used in industry. And they test their grade automatically, and they know exactly which temperature, what the cooling rate they need to apply to reach the hardness that they would like, you know, to prevent oil crystallization and so on. I do not enter in metallurgy, but anyway. So, but this is an example of it's already applied. It's just a matter of where is the money. If the money is coming from data, for thermodynamic data, I'm sure the model will be developed. It's just a question of matter of money. Just ask Anis, Allah she's smiling, but I'm sure if they have more money, they could develop all of this. It's just a question of matter of money, I think. For medicine, it's done. For science, which are in which your money is done. Like for example, now we are moving quantum dot in catalysis. Come on, so we are doing a metal catalyst, you know, single atom catalyst. So we can try to do this, and we are doing plasmolytic reaction. Means we have this kinetics for. So it's just a question of money, I think, to be honest. Yeah.
Okay. Thank you, Johan. I see the audience is getting restless here, and we had like 3 raised hands, including Ala, 4 with
okay.
Ala. So I just suggest now, because we're supposed to.
I would answer very quickly. Okay.
Which I'll give the floor over to everyone, would turn into 8 o'clock. Suggest that all of you that have questions or comments, please contact one in writing. If you mind, because time. Okay. So Dr. Sipola already has a mic, so I'll let you ask the last question.
Please. I just write on my email address just in case. Yeah. Question?
So all data which we got is theory-based. For example, we have changed the standard pressure and standard entropy, and we might even change how we interpret some experimental data. So if we have a database already, and then we produce these new values, will they be rejected as wrong because the theory in the background has changed? And how can you clean up your database in this kind of case?
So, but basically, when we have such a problem, I will give you a sample example. So we start with properties and some materials that we have in in our database, and we collect a new data set, for example, for the same property and the same substances. And we find a way to extract the data from the recommendation itself. So means if the recommendation change for a given property, you just need to align this, and the software itself will ignore the data that they are not following the chain. You understand my point? And if we have to recalculate somehow a property because of XYZ change in science or on a way to analyze data, we can also implement. You take my point. It's just a matter of code. It's coding.
Thank you so much. I'll give over to Simao to conclude this session. Thank you once more ever again, because you've been a wonderful crowd. Thank you.
So thank you very much. I won't talk that much now. Thank you for being here, for all the speakers that did a very interesting job, and for all the fruitful discussions. I have to share with you, if you want, you can go to the IUPAC page, and you will have these presentations also there as a video, so you can really go into it again and ask the questions to the people directly. And finally, just to tell you that Chemistry International has just published a very short summary about this conference, about this workshop. So thank you for being here, and all courageous people, not only here, but at home. And thank you, Hale and Johan and Vladimir, for being for so long doing your, for so far doing your presentations. Thank you very much for being here.
Thank you very much.
Thank you.